Mhm. I
Perfect.
never
That is what
did
we want to hear.
never did practice, but whatever.
Oh, that's right.
Oh
Sorry.
yeah, you gotta make me
I do. We're recording all of this. That's awesome. You're right. Here we go.
this is us. The real us.
And where are you? There you are. Maybe I'll
Sure.
edit this part. Oh, I was just confirming you. There we go. All right. I might edit this part. I think you're good.
Yeah.
Let's let them all in.
All right.
It is still 5 o'clock, just I think. The top of the hour is about to go past us.
Did you leave me? Okay.
I think so.
Yeah.
But we were so busy chatting about all the amazing math things in the world that I didn't get a chance to make Rachel our host. Welcome to session 3. This one's computational fluency, multiplication, division, fractions, decimals. Oh my, as I said last week. I'm going to leave the tech chat, the tech time, just I'm going to pop it into the chat because I think you're all pretty familiar with the reactions at the bottom, which are always lovely to see float up the screen as we move through. My name is Mardell, and I am your outdoor learning school and store host. I come to you from the unceded territory of the Ktunaxa. In the traditional district of Gukan Amakas, from the community Kagawakamituk, which is where the waters come towards you. If you would like to put a land acknowledgement in the chat, we always appreciate that. It's an important part of where we are in place and space. And so, yeah, I'm going to pass it on to, again, the main event, which is Rachel. And we know we're in excellent hands because she has done such amazing work the last couple of weeks. We were just chatting about how many people are heading into the recordings, and that is lovely to see. And so we're going to have Rachel take it away.
All right. Hang on. I'm just fixing my screens here so that I can see my slides in the presenter view because that way I have my little timer. All right. So here we are again, week 3, and we're going to dive into multiplication, division, some fractions with multiplication and division, and a little bit of decimals. I also threw in some ratios. So lots of good stuff today. I'm excited to get going here. I'm back home, and I like to acknowledge that the land where I live and work, and I am today, exists within the unceded territory of the Gayakono, members of the Haudenosaunee Confederacy, and I'm very grateful for their stewardship of this place throughout the centuries as well as today. And this is a nice little kind of like a toddler land acknowledgement of thanks to the land. I just think it's very cute. It's from the Canadian Center of Outdoor Play in Ottawa. If you ever get a chance to tour their facility or go to the play conference, highly recommend it. It was an amazing conference as well as their facility. It's amazing. They have a beautiful building and beautiful outdoor classrooms. Um, so here's the computational fluency slide that we showed last week when we were talking about addition and subtraction. And this week, we're going to be hitting the ones that are in red. So the multiplication, division in groups, arrays, sharing, um, multiplication and division facts, division concepts, all of these lovely things to kind of, it's a big focus area over many years in the elementary primary years. So I wanted to make sure that we had plenty of time to cover it. So I like to always start by building a shared understanding so that we all kind of have a similar background and understanding. Even if we've been teaching a long time, sometimes we don't have a complete understanding of the theory or the, I don't know, instructional methods that are happening. And so I kind of like to bring that out and connect that for you. But we've talked a little bit about this before, that until now, children have engaged in additive thinking. They're counting by ones, numbers are static. They're adding and subtracting, thinking about how many more, how much longer. But as children encounter multiplicative problems, counting by ones becomes super inefficient, right? And students begin to develop better ways to keep track. And typically, that's where we start seeing skip counting, right? Um, what we want them to do is skip counting itself can be kind of additive when they're thinking about 7 plus 7 plus 7 plus 7. But we want them, and we've talked about this a bit too, but now it's the big deal, the unitizing, the ability to see something made up of separate parts as a single unit. And we really introduce this when we start thinking about place value as a group of 10. But now groups can be any size, right? So 4 is 4 ones, but can also be a unit of 4. And I can go for 8, right? We can also group those units. That's an important part of multiplication. Each group is a unit of 4. But also multiplication has other processes like scaling and comparing things proportionally, things like ratios, etc. So there's more than just units and groups and arrays. But one thing I do want to say here is that this multiplicative thinking, and I think I've said it before, maybe in the first one, is the foundation of multiplication, division, fractions, decimals, ratios, proportions, linear functions, which are all central to algebra. So we're really building those blocks right here, right now for later math. And this is, if we have a strong foundation here, we're really setting up kids for success later on in upper level math. And upper level math gives kids access to lots of different career choices, et cetera, STEM, et cetera. All right, so we understand the importance of unitizing, and we know that there's a set of facts, right, that we need kids to become fluent with. So here are, I think I have 5 tips for helping students recognize, to unitize and move towards fact fluency. So the first one is helping students recognize equal groups and to unitize. Surprise, surprise there. And this is the part I like to think about. So this thinking, the switch from additive to multiplicative is signaled by a change in language. So they start saying, instead of 4 and 4, they say there's 2 4s. And we can model this language early, saying 2 3s, 3 rows of, right? And so we can start modeling that language that shows them the units and the groups to help them kind of start thinking that way. And some of the instructional routines that can help support this, things that we've already talked about, like quick looks and counting collections, can help kids recognize equal groups. So quick looks are the ones I kind of put on the bottom here. Is, remember I showed you these dominoes, right? That can be a quick look image, and we're looking and hoping and pushing kids towards seeing those as groups of 5 or groups of 10. And then even things like the boots, right? Those are in groups of 2. They come in pairs. And so that could be a unit, and that could help us count those boots, right? And then here it is an example in nature, right? These berries are growing in groups of 4. So pointing them out and using images like that as quick looks can be a way we can support that. And I think I have some counting collections examples. The second tip is, and I didn't make these tips up. This is from the literature. And I love this one because it says, look for groups in the real world. Yes, that's exactly what I want you to do. Go outside and look for groups in the real world. And I put some examples, including this weird picture of me talking to students. I love teaching pictures because you're always like in a weird like face or look. Like, I don't know, you're never like looking at the camera, right? You're just not, you're teaching. It's fine. But I have a horse chestnut leaf, which comes in a group of 5, is what I'm doing. Because we were on a walk looking for things in groups. But there's lots of other compound leaves, is what these are that's a whole leaflet and it has smaller leaves. And then clover. You can talk about bird nests. Birds usually lay a certain number of eggs. You can look at animal tracks and bird tracks and petals. These are apple blossoms. So those are coming out hopefully soon, maybe like 2 months. But hey, I can think of it's going to be soon. We have snowdrops, but they're covered in snow now. This instructional routine, the math walk, which is the picture I was holding the horse chestnut leaf. Um, this is how I set it up. So I have this piece of paper. I'm really famous for my ugly worksheets when I'm actually working with students. And, this is like spatial awareness, turning your paper horizontal, drawing the columns so that we have enough spots, labeling our columns 2, 3, 4, and 5. Then we put an example of something that comes in twos, threes, fours, fives, and sixes. And then we went outside, and this is in a more urban area, looking for things that grow and come in groups. And we recorded them as we went. And I wasn't very picky about it. As long as they were doing the math, that was my goal. And yeah, it was very exciting. We saw a cat, which had a lot of different things, including 2 ears, but 4 legs. It was very exciting. So think about that. Squirrel would have 4 legs, 2 ears. Um, Number 3, using manipulatives and models to build an understanding of doubling. So we talked a little bit about doubling. Here it comes again. We talked about doubling last week in addition, and using it as a strategy. Now we're thinking about doubling as a multiplicative thinking, and doubling our unit. So using manipulatives to model that, much like we did with addition. And we want to progress here to tripling and quadrupling. So quadrupling is doubling and quadrupling are strategies that we can use with multiplication facts, our twos and our fours. Double facts is what I call them. I'll show those to you in a minute. And so we really want to get them kind of fluent in doing that. And that's helping them see the connection between those facts, and build strategies and build off those addition strategies they have, but translate it into multiplication. Remember, we're trying to build relationship between facts and see the connections, to build fluency. And I'm going to talk more about that as we go here, but just as an aside. Number 4, model multiplication situations using manipulatives, but this time with lots of groups. So here's where your counting collection comes from. Here I have some apples. Here these are those jar rings that, like, for canning. They work really great for grouping things, whether you're outside in the snow, those are in the snow, or not. So I really like those to help kids group. There's skip counting trains, and these trains are done on leaves. We saw these a little bit before in our counting day, but here they are again. Now we're pushing them to think more in units, right? And then we can bring our 10 frames back. So here we have some apple blossoms. I wouldn't suggest this on a class scale of 25 kids, but whatever is abundant, if there's something abundant, you can use it in a 10 frame. You can also put objects, more than one object in a 10 frame. So you could put like 3 stones in each box, and that can help kids also make some connections between that 10 frame model tool they used and multiplication. We also use those boxes in literacy a lot for sound boxes, and we always say, one sound can go in box. It could be 2 letters in one sound. This is the same thing. It can be 3 items in one box, right? But it's one unit crossover. Another great context here for multiplication is animal tracks, and I showed those a little bit earlier. But thinking about how the number of toes can be a unit, how the shape and the distance between tracks and pattern can help us identify those animal tracks, how many toes in X amount of paw footprints. So if you have a whole string, right, we can think about how many toes prints were in that whole string. And then you can also extend it to think about the stories that the tracks are telling. Was there a kerfluffle? Were there more than one animal? Were there more than one type of animal? Were they going somewhere? Were they moving quickly? Were they moving slowly? Were they hunting something? All of these things we can kind of infer from the animal tracks, which is a great literacy crossover. I was just saying, I was sharing, I've been doing a lot with literacy this morning, so I'm making all these connections in my brain as I'm doing this. And number five is introducing the array, rows and columns. I love, love, love arrays. I don't know why. Maybe it's because when I show them to kids, they start seeing them all over and they get very excited. It's also kind of a great tool and model that we can use and keep using to scaffold our learning as we get into larger numbers, which I'll show you. So lots of arrays here that we can make. We can make them in muffin tins. We can make them with rocks and pine cones. Often seed trays come in arrays, which can be a great real life example. Um, Again, the math walk is a great instructional routine, especially if you have some human-made environmental aspects. Arrays are easier found in more human-built environments. Although I was talking on Monday with a group of teachers in Saskatchewan, a very rural school, and we even found some arrays outside of their school, on their building, on their school bus, on the house across the street. So they really are almost everywhere. If there's just a little bit, the playground. Here we were at the county like court building, and they have these bars over the windows, which is something. What I do is I give kids graph paper and they bring a pencil and a clipboard, again, fancy worksheets here. And I have them walk around and we find arrays. And so when we find array, we use our graph paper and we draw the array out using our graph paper, and we figure out the answer of how many squares that is, and we write it in the center. And then they start seeing them everywhere and they get very, very excited. And as we get to bigger numbers, I will show you an example from this particular walk where the kids got really into it. And things like grates, but even natural things that you can kind of stretch into being an array, like this leaf with the double leaves all the way around could be 2 by, I don't know, 10 array there. So you really do start seeing them everywhere. And then we can also use arrays. And I couldn't remember if I had brought this up in fractions last week, and I don't think I did because it's kind of multiplicative. But we can use arrays to find factors, and factors are really important to find if something's divisible by something and for common denominators. So I wish I had known this trick when I was a kid. It's not really a trick, but so you take a set of things like 16 and you can use it to figure out the factors. So the first thing you would do is make a 1 by 16 array. And I don't know about you, but I was taught to write 1 and 16 and leave a space in between. And then you want to find the next factors. And usually we're told to try like 2, right? But if we have a line of actual materials that's 1 by 16, we can just cut that in half. And that gives us this picture right here. So that gives us the 2 by 8. So we took our 1 by 16 and we folded it in half and we made a 2 by 8. And so now I fill in my little, I have 1, 2, 8, and 16. And I leave a little space because I'm not sure if I'm done yet. And now I can fold that into half, and that gives me a 4 by 4. And since it's square, and I can't make any more arrays with my materials, I know I'm done. And so for me, as a child, I was like, am I done? I never knew if I was really done. Maybe there was some more numbers. That was always hard for me. How much space do I leave between? This is a very concrete way to use arrays and natural materials to figure out factors and make those connections between arrays and factors and divisibility. Once students have understood this idea of equal groups and unitizing, those are all ideas to help them see that, they can begin to explore the patterns and the relationships between multiplication facts. This is important because we want children to reason about these relationships among facts to build that fluency. It's a much more powerful approach than just having kids memorize facts. And I have, in a couple slides, I have some research that backs that up. Because it fosters that deep conceptual understanding. When you're noticing the patterns and you're seeing the relationships between facts, you're understanding the why and the how, and that sticks better than memorizing, and you're better able to apply that knowledge to solve problems. So this is a hundreds chart. And I think it's the nines facts. And so we were looking at the patterns of the nines facts here. Um, this one is twos. So asking kids to find these patterns, often in the classroom, I did this on graph paper. Or on not graph paper, but like on copies of the hundreds chart. You can do it outdoors on a fabric hundreds chart like this, or a chalk hundreds chart, or you can bring laminated hundreds chart and use dry erase markers or crayons as well to do this. But asking kids, what do they notice? What patterns do you see? There's more than just the two patterns. And this one particularly makes lines, right? The nines made that diagonal that repeats that diagonal if you kept going. Then asking them to describe the patterns that they see with their words, numbers, and symbols. So kind of verbalizing and showing those patterns in different representations, which we know is important. We also can help children see the connections between facts with the array model. So here we have an array of 4 by 5, and we also have an array of 5 by 5. Notice I took my plastic manipulatives outside, and the math is the same as if I used rocks. So we're just showing here that if we can figure out 4 times 5, we're just adding another group. Similar, we start noticing arrays in places like egg cartons, right? And so this egg carton has more than my typical egg carton, but really we just added another group of 6 here. So thinking about what do you notice about that? Is there a pattern here, etc. And notice let me go back. I started writing and kind of making an open array here because we're going to start pushing kids that way. And then going back to our doubling and quadrupling, using the array model to highlight how facts featuring those aspects are related can be helpful for them to see it in another way. Remember, we're always thinking about representing these things in different ways, seeing patterns and making connections. So here it is with the array. And then that quick look routine, again, can be helpful here when we're showing kids the connections between facts by showing them images of a group. So I might show them this image of a group of 4, and then I might show them this image of 2 groups of 4. I'm using language here on purpose, asking them what they notice. Oh, it doubled, right? That could be something kids say. Kids might say, oh, now there's 2 groups of 4, or 4 groups of 2. And then I show another one, and it could be this or even more of them. Now, what do you see? Tell me what you see. How would you write this mathematically, right? And so we're using that same instructional routine that we started way back, but now we're using it to help kids look at things in groups. Because remember, this is a quick look, so you don't have time to count. So this is an image from Wild Math, grade 3, and it's the strategies that I recommend teaching and I walk kind of through in that resource. But the reason I put it on here is it's a nice summary of some of the main strategies that kids use. I highlighted all of the ones that involve doubles, just so you can see how many that involves. And when we're thinking about why we would teach kids strategies and help them evolve some of their own strategies is when we look at the research, it's pretty clear that strategy groups outperform and retain facts better than non-strategy groups, since non-strategy groups refer to those that are memorizing primarily. So that there's a lot of studies that support that. Strategy use also predicts success in overall math achievement. So kids that are able to use strategies versus just memorizing the facts are better at math overall. They're better problem solvers, more creative thinkers, can solve more complex problems. Strategy instruction first teaches students to use the relevant strategies and then how to choose the strategy. So you would want to put emphasis on would a doubles strategy be a good idea with this fact? Well, maybe if it's a 4's fact, right? Double, double, but maybe not so much with a 5's fact, right? So we want to teach kids strategies, but we also want to teach them how, like, the appropriate time that maybe this strategy or what couple of strategies would apply to this problem. So being able to choose an appropriate strategy is important. And you can ask them questions. When might you use this double strategy? Or what strategies are you thinking of using for this problem? But that's an important kind of best practice. And the reason that we encourage kids to come up with strategies, but we also want to kind of balance some explicit teaching of these strategies, is that every student should have access to basic strategies, which often means we have to explicitly teach them. It doesn't have to be overbearing. It can be very quick and it can be organic out of kids' examples, but it is a best practice for teaching addition, subtraction, multiplication, division facts. Kids don't always on their own connect multiplication actions or situations with the symbols or equations. So we want to make sure that we're modeling this, perhaps explicitly teaching it if needed, always reading the students that you have. Every group is different. And then providing opportunities that are using and going from a model to that more abstract notation using symbols and equations. So here we found a daffodil that has 6 petals, and we then wrote and drew all of the facts in that fact family. Similarly, this is those apple blossoms. So we found the blossoms, we figured out how many there were, and then we represented it with plastic numbers, the equation. Sometimes plastic numbers are, well, I love plastic numbers, first of all. They're lightweight, they can get wet, etc. But depending on the student, sometimes the writing can be overwhelming. And so if we're focusing on the math, the plastic letters can take away some of that cognitive load, or if you have kids with dysgraphia. So they can be a helpful scaffold if you're focusing on math and the writing is getting in the way. Just a thought from my special ed brain. Division. So we're moving for division. We want to introduce the relationship between multiplication and division fairly soon. We don't want to like isolate the two into two different things. And we want to provide lots of opportunities. I mean, I feel like I'm kind of like a broken record tonight, but lots of opportunities to represent division. And there's 2 main types of division problems you want to make sure that you're exposing your kids to: how many in a group and how many groups, and give them lots of, just like we did with addition and subtraction, lots of opportunities to feel that out. These 2 books are really great. One is about remainders, and we also want to invite remainders in. Remainders are natural. They give us plenty to talk about and think about. What do we do with the remainders? Well, it changes with context, right? Maybe I have one left over and I break it in half. Maybe I have one left over and I need another box, right? Or another bag. Lots of fun conversations about remainders because they have meaning. They're not just remainder 2. We had skip counting trains for multiplication and unitizing. Now we can make trains. So taking natural materials or also Unifix blocks are really fun for this activity and go outside perfectly fine. You make a long train, and then you divide that train into something. You can roll a die, but then those cars have to have that many people in it. And so then you can have kids connect that to the equation and write that out, or write a problem for that, etc. But it's a great way to kind of emphasize that we're dividing into groups. And then what happens if there's leftovers? Making rows, I love this. It kind of connects to that traditional, division notation with this little box. I don't actually know what it's called. But it's kind of a crossover between hands-on manipulatives and actual division notation. And so you roll a die. I have these like little laminated strips, and you roll a die, and that's the divisor. So I rolled a 3, and so I was doing the 14 divided by 3. And so I had 14 items, and then I started putting them in groups of 3 until I couldn't make another whole row of 3. So that was my remainder. So I have 4 rows, that's my answer, and remainder 2, very concrete. And then I write it on my little sheet. You could have these as paper and have them as evidence of student work. I have them laminated so that I can reuse them. You can put your name on them and they could still hand them in. And you could take pictures of them or record them somehow. Um, or just review their work at the end as kind of like an exit ticket. But that's also a way to kind of assess what's going on. I like the laminated ones because they can get wet. So there's that added bonus, depending on weather conditions. But this is a great activity, and it's inspired by an activity by Kathy Richardson, if you're familiar with her work. I have another one, some context here. How many knots on a rope? So giving each student or group of students a nice piece of rope, and asking them how long is the rope. I also give them a ruler, and then having them tie one knot, and then figuring out from there how the length of rope needed for that knot, and then estimating how many knots they think will fit on that rope based on that measurement. So they're kind of unitizing that measurement all the way down that rope, and they're estimating using division and multiplicative thinking, and then they're going to do it. And there's some variables here, right? And so it gives us a lot to talk about. Was the answer that you estimated right? Was it close? Or was it way off? And sometimes kids, their knots are like spread out. And it's like, well, could you fit another knot in there? Or, this is cotton rope. It kind of is a bit stretchy. There's a little bit on the end that's kind of sticking out. But all of this is real life. And so real life variables affect our answers. And so it gives us lots of rich math talk, but it's also thinking about division. And then we talked about this instructional routine number strings. So here it is again. This particular number string, the one that starts with 3 times 8, is particularly selected to help kids see the connection and relationship between multiplication and division, because they can seem like 2 different concepts. And so this is kind of helping them see those connections. And then the string with the leaves, this is a way you can also bring them outside with natural materials, is you can just write on leaves with a Sharpie, by the way. This string is helping students see the pattern that occurs when multiplying by multiples of 10, which is a very important strategy. Again, we're building off our knowledge of 10 as a benchmark number, which we focused on a lot in addition and subtraction. And here we're applying it to multiplication. And so we're showing how that changes and how it becomes a pattern. What do you notice? And then you can apply it to other problems. Here's that counting collections, but now we're looking at it with a multiplication and division lens, having them collect a certain number of objects, creating a single array with those objects, then creating a combination of arrays that equals, so 2 different arrays that still uses all of those same materials. And then drawing a picture and writing an equation for representing your work. You can also have them tell you how many more you would have if you doubled it, how many you would have if you divided it or quadrupled it, right? If you divided the whole collection by 3, for example. Lots of opportunities with this basic instructional routine that we've been talking about since week 1. I like to make it connective. So now that we have a pretty good solid understanding, we're going to move into multiplying larger numbers. And this is that picture that I was telling you about during our math walk. And I can't remember if I talked about this in the first week. I've done a lot of math in the last couple of weeks with a lot of different teachers, so it's all kind of blending. But this is the kind of like it's in an like a sidewalk going over like towards a crosswalk. So it's meant for visually impaired people to tell them that there is a road that's like the crosswalk and that you need to be careful. And so it's like this raised array of dots, but it's big. I'm standing there, those are my shoes, because that's the road, and I'm trying to keep the kids out of the road because they're excited about this very large array that they just found, and they're trying to fit it on their graph paper. But I know, and you know, that that's not going to fit on their graph paper. So it led to us a great conversation about, well, what are we going to do? We can't stay in the road all this forever. Like we're going to get beeped at. People are going to get concerned. They're not actually in the road, but people get crazy. Um, and so what are we going to do? We need a shortcut. We need a strategy. This is a big array. We cannot sit here and count. We need a more efficient way. And so it naturally led, so people figured out, kids, that maybe we should just figure out how many there are on one end and how many there are on the long end and write it down on our paper, and then we can figure it out when we get back to our classroom. And that's what we did. We got out some bigger graph paper. We got out more of those plastic cubes. And then we, started figuring out that if we could just multiply the sides, we could split it up into smaller ones, and that's where we want them to go. So seeing a big array like that or a big multiplication problem like that, we can break it up into arrays that are smaller and easier to work with. And we did this with decomposing and composing numbers with addition and subtraction. Here we're applying that same idea now to multiplication. So we can break this big array up into two different arrays that are easier. Notice we picked one that had a 10 because that's an easy number. Here it is again. And then we can just add that smaller one in to find the total number of dots in this array. And so this is leading, and you can see the drawing here is leading towards the open array model, which like our open number line we talked about last week, is first used to represent our thinking, but then we can actually use it to help us solve problems as a tool. And so we're trying to push kids that way. They were making arrays with all the dots and using graph paper and using materials, but we want them to move to actually using it as a tool to solve problems like this right here. And here's that array that I had before, and here's kind of an open array model. So if you're talking to students about what was going on here, and you can draw and start modeling that open array to describe the thinking that was going on. It's like, oh, well, you had a 4 by 5, that was 20, and then you added one more row of 5, and that's what that looks like with an open array. So we're moving from that visual array to the open array, and this is going to come back, and this is why I'm emphasizing this. Here's some context. I did this in New Brunswick last week. We had a great time. I pose a realistic nature kind of problem to my students. They know I really like nature, and so I either say I have a really cool, it's a larger problem than this. So I have a whole nature collection and I have different categories, but this one I have just rocks. So I've been collecting rocks for a while. I have a big collection. There's lots of colors, sparkly ones, like you make it fun, right? They can really imagine it, make it rich. And I have 136 rocks in my collection, and I want to display it so I can show it to my friends and my students. And I have this wooden box that's 2 by 5, so it's 10 on purpose. It's 10. And I want to use these boxes to display my rock collection. And I asked the students to help me figure out how many boxes I would need to display my rock collection. And the idea here is I'm asking them I give them a laminated version of this box. It's just a 10 frame, and they can use that as a blueprint to help them figure it out. And I'm encouraging the use of a benchmark 10 array in seeing that unit in 10 to make their math easier and connect it to multiplication. and division. And then once they figure out how many that I would need, and there are leftovers, so they have to figure that out, then each box costs $10. So they're going to be hopefully multiplying, somebody will, multiplying by 10 to get the number of boxes by 10. So again, I'm encouraging and moving them in that direction to notice that. And then you can also have an extension where they take those blueprints of those 10 frames and figure out different arrangements. And kids really they get very creative of how I should arrange these boxes when they come to make my collection look the best it can. And that's now putting them together in bigger arrays, right? So rich context can go a lot far. This is a similar idea. Here, the benchmark 10, we have 10 threes in one of our 10 frames, which is 30. So we're kind of modeling how that would look. But we're using it to solve the problem 17 times 3. So we decomposed that 17 and we modeled it with our 10 frames to figure out the answer to the problem. And then we can also reconfigure these facts in different combinations to make different multiplication problems. We can make even larger ones. And so we can start seeing how we can decompose and compose things and use the facts we do know to figure out the facts we don't know or even larger problems. So that's kind of how that scaffolds. There are a lot of multi-digit multiplication strategies that we encourage kids to move towards. They will be naturally moving towards this area method and the partial products because we're breaking apart numbers and we're breaking apart arrays. I usually wait to teach the traditional model until very, very last because it is an algorithm. It is not building conceptual understanding. The other one I like to teach is lattice method. I have a slide on that. It is typically my students' favorite one. I also really like the area method. But again, when we're teaching strategies, we also want to say, when might you use this strategy? Which strategy might be best? So for like that 17 times 3 problem, it's kind of a waste of time to do lattice, right? We can easily kind of use a partial products method on that one. So that might be a more appropriate one. So here's that open array. And you can see how now it's translating to the area model here. So the area model, sometimes called the box model, is great. We're decomposing the numbers, and then we're multiplying each number in each box, and then we add them all up, and that's the answer. Less mistakes, easier numbers. It's a great, great strategy for a lot of kids, but you can see how that open array work. First the array, then the open array, and now we have that area method is kind of all on a trajectory, right? We're moving kids that direction. And then if you're not familiar with the lattice method, I highly suggest you check it out. It's quite fun. It's kind of like the box method, but you draw a box, and the great thing is you can do this anywhere, just like you can do the standard algorithm anywhere. You draw the box, you draw the diagonals, you multiply, or you multiply and then put them in the two boxes. So like 3 times 1, and then you put a 0 and then a 3. 3 times 4, you put a 12, so it's 1 and a 2. And then you add along the diagonals, and you can carry if you have to. But here's some examples of the lattice going outside. So it doesn't mean that we can't bring this strategy outside, even in the snow. All right, friends, we're rolling into fractions. This is where everyone starts having a heart attack, but this is really fun. I, like you, probably did not enjoy fractions as a student, but I do enjoy fractions when I get to do it with manipulatives and natural materials, and most famously, mud pies. So we're starting here with multiplying whole numbers and fractions. The language here is helpful in scaffolding and thinking about it. So, 1/4 of 12, right? So I have 12 items, and I can either think of it in like 4 columns and just taking 1/4 of that. So that's 3 of the items. Or you can think of taking 1 out of 4, 1 out of 4, 1 out of 4 in each one of those rows, either way. So that total is 3. Um, what's interesting when we're multiplying and dividing by fractions is that our numbers are not always getting bigger, right? As they do in regular multiplication. And so that's something to think about and notice. And here's a similar one, 12 times 1/4. Here's that unitizing thinking that we wanted kids to have. The unit now we're multiplying is we're making that iteration. We talked about that in number sense, I think, the first week. We're iterating that 1/4 12 times. And then we're adding up all those fourths, right? And so we got 4 of them makes a whole, 4 of them makes a whole, 4 of them makes a whole. So we get that answer of 3. So a different way to think about it. But not so hard, right? When you are actually thinking about the concepts. If we taught kids just to multiply across, that's an algorithm and it's not reasoning about what's going on in the math and the fractions and the thinking. And that's what we want them to do. As soon as we teach them the algorithm, they're just thinking about the algorithm, and all actual reasoning ends and no fraction sense is happening. So I urge you to hold off on that as long as you can. And they will eventually probably figure that algorithm out on their own, and we eventually will teach it. But all right, here it comes, multiplying a fraction by a fraction with mud pies. And they don't have to be mud pies. I definitely showed last week in snow in there, right? I've used pine needles, grass, all kinds of things. Salt, if you're happen to be inside. One day we had to go inside because there was like some kind of like weird chemical smell. I was like, this is not, no, we have to go back inside. It's very sad, but it happened. It happens. Or wildfires, that happens, so whatever you have to use, but the idea is the same. So here's the problem. 1/2 times 1/4, or 1/2, 1/4 of 1/2. So first you take the first fraction and you make 1/2 and you mark it off with something. And I usually use grass or leaves or whatever I have. And then we go back in the other direction with the other fraction. So now we're going to cut it the other way in fourths. So you can see in that picture, there's 1 leaf. So a fourth of that pan would actually have 2 leaves on it, right? That would be a fourth of the pan. But the leaf is marking where they overlap. And that's the answer. So now we can look at the total number of parts we have. We have eighths. And the part that overlaps is 1/8. So that is the answer. I know. It's amazing. Because that's 1/4 of 1/2. That was a lot easier, I thought, than, remembering another algorithm. But I think it's also more fun. We can also divide fractions with other models, and we'll come back to, I see some hearts. We'll come back to dividing fractions with mud pies. Don't worry, it can be done. So here, this is always fun because now we're dividing something by a fraction. The number gets bigger. It's very interesting. So lots to talk about. 4 divided by 1/2. So here are 4 leaves, and we're dividing each leaf into half. So now how many halves do we have? Well, we have 8 halves. We can do the same thing with 6. 3 divided by a third, 9, right? We have 9 thirds. You can also divide with like manipulatives, kind of like a set model. So 6 divided by 3/4. So I made fourths 6 times. And then I took 3/4 each one, and I kind of reconfigured them all into 3/4. This one actually happened to be no leftovers. And I got 8. So there's 1, 2, 3, 4, 5, 6, 7, 8. Different ways to do it. What do you notice? Fraction division using other models. You can use the stick model. We kind of did some of that before, but here 1/2, this is a fraction divided by a whole number. So it's the opposite. 1/2 divided by 4. So I have a half a stick. That's that first number line. And I put that stick there. And I'm going to divide that half into 4. And so I divided that part of the number line into fourths, and that's really eighths. So 1/2, or dividing half into 4 parts, is an eighth. That makes sense. It's a little abstract, but I liked my problem because it's kind of unrealistic. If Rachel has half of a sandwich left and she wants to share it with 4 teens, how much does each teen get? This is unrealistic. There would be like some kind of like huge like kerfluffle over eating an eighth of a sandwich, I'm telling you, as a mom of 3 teen boys. Okay, here's where the fun begins. And I didn't actually use pies to explain this with pictures. One, it just takes a lot of slides, but it's easier to see this way. But I encourage you to try this out at home. So 2/3 divided by 1/2. Ready? Here we go. So this requires 2 pans. So pan A is 2/3. And so we do that horizontally, just like we did with multiplication. And then we do the other pan in halves. Okay. And so then we're going to want to do what we really call usually is like making a common denominator. We're going to, I like to think of it as the pan A, I'm going to now cut in half because my pan B is halves. And then pan B, I'm going to cut in thirds. And so we end up having sixths, right? But that works every time. I don't know. So we have everything is now in sixths, and we have our 2 different pans. What we need to do is determine how many halves the 3 green squares fit into 2/3. So we can fit 3 of them, which is a whole, into that orange part, right? So that's 1. But we have 1/3 left over. Does that make sense? It's kind of confusing. So we can fit one, the unit is that 1/2, but we're trying to fit it over here into those 2/3. So we have like 1, 2, 3 is full, and then the third is left. We have to figure out what the third is. The third is really, it's just that it looks like 1/6, but it's a third of the half. That's why it's a third. It's confusing. It does make sense if you try it out. And I encourage you to try it out. And if you're still stuck, you can email me. Trust me. Just trust me. I have some videos of it, and I could make another video of it. But and you can also play around with it on paper. But I really encourage you to give it a shot because it does make sense, and it's pretty interesting. And it's much better than the keep, change, flip, I think is what you usually teach. Keep, change, flip. So you change this to multiplication and you flip this. And the reason you flip this is because it's 2/3 divided by 1/2. And to get rid of the fraction on the bottom, you multiply by 1/2, the reciprocal. And so that's how it becomes multiplication. It's a whole thing. I never knew that as a child, just being real. So we're going to move on now to ratios because, there's more to life than fractions, but they're related to fractions. So context, roots and shoots, and younger kids can do this one as well. Measuring and comparing the lengths of the roots and the shoots of a plant, and different plants put different amounts of energy into their roots versus their shoots, which is a great way to talk about why would they do that? What's the advantages of either strategy? And you can compare and figure out the ratio of the roots to shoots with older kids. There's this book called Tops and Bottoms, which is kind of a trickster tale that's kind of playing off the differences between roots and shoots of different plants, garden plants. And you can also convert your ratio to a decimal and compare plants that way. So that can be a fun context. Another one is turbidity. So creating different ratios of mud versus water. So this is a bit messy. You're going to need a lot of recyclables to mix your ratios of water. But you're going to have kids estimate what ratio of mud to water will match the number 5 or 3 on the turbidity scale. These were chosen because 3 is the beginning of healthy conditions for fish. So how can we get to that turbidity? Can you estimate what ratio of mud to water will be clear enough to see through? That is what turbidity is. It's a measure of how opaque it is that we can see through. So start with a 1-to-1 ratio of mud or sand to water, then a 2-by-2-to-1, 3-to-1, etc. And they can construct a table with the ratios and their descriptions and drawings and compare it to the turbidity chart to see if fish gills will get clogged, water starts to lose oxygen at certain numbers on the chart. So that can be a fun connection. Similarly, in wild math, I have this one, color mixing. So trying to choosing a palette, a color like blue or green, and doing different ratios of white and the base color. And then kind of making a key for each one of these ratios. And then I always have them like make some creative names for their colors, and naming their colors can be really fun. And this is an important conversation in real life context because often we want to recreate a color, and we have color codes on our computers so that we can recreate the same color. We have to buy colors, or we want fabric to be dyed in the same color, right? We have to know the ratio of pigment to whatever are mixing in our base. So it is a real, if we want something to be reproducible, whether in a recipe or a color, we need to have kind of a ratio that makes it more repeatable, like a recipe. I got an email about maple syrup season today, and here it is. So I had already had this in there. There's lots and lots of ways we can connect if you live in a place that is doing maple syrup season. Right now, it is maple syrup season where I am. But here I brought it in for the ratio. 40 gallons of sap is needed to make 1 gallon of syrup. That's the ratio I've learned. And then, so you can use that as a base ratio. And for talking about ratio, it's a very real life context. And thinking about how many gallons of sap do we need to make 8 gallons of syrup? And the numbers get very big very fast, right? Thinking about the rate of sap flow, hours per volume, whether you're measuring in milliliters or, I don't know, pints. And then you can also think about the money part and the volume part. So what is the price per gallon or liter? If I have 2,500 milliliter containers and I have X amount of syrup, how many will I be able to fill? Will I have one that's half full, remainder? What do I do with that? I make pancakes. That's a different context. So what do you do with leftovers? You make candy out of it. I mean, there's lots of things. This is another one I like to encourage. People often ask me, what do you do in the winter? What do you do in the winter? There's lots of things you can do in the winter. Here's one of them. Sledding often is a great way to measure the speed. So you get some timers. They sell like kid primary timers. Often a lot of watches have timers on them. And you measure, you mark a start and you mark a stop, and you measure the time it gets from there to there, and then you measure the distance. And so you can calculate the speed, right? This is generally for older kids. Or you could just record the times too and see which one's the fastest. But what is the speed? What's the fastest we can go? Does the number of people change the speed? So what kind of conditions variables enter here to change the speed? And talking about that and getting into the kind of the physics. Is it getting more packed down, right? Try it on a very icy day. You're going to go a lot faster. You can also do a similar thing if you don't have snow or it's a different time of year, taking how long it takes to walk 10 meters. I've seen people do it with like a skateboard or scooters, and calculating how long it would take to walk a kilometer. You can also do this with like rolling things down slides on the playground, or like toy cars, and different weighted cars can be another way to do this. And of course, when we're bringing in time, we're bringing in decimals as well. So whenever we have measurement and that kind of thing, we can easily bring in those decimals. And then similarly related to ratio rates, rates are also everywhere. We can do the rate of stream flow. We can do parking costs. So on our walks, we often saw parking meters, and that got talking about how much it would be to park for 2 hours or 5 days, and how quickly it adds up. Temperature change over 12 or 24 hours. If you know there's like a nice cold front or warm front coming through, that can be a really interesting um, recording the temperature, graphing it, and then calculating the rate of change. Um, Amount of bird seed needed each day. If you have a bird feeder, a lot of people have bird feeders on their classroom windows or outside their window door or their classroom door. And if it's someone's job to be filling or their chicken feed, a lot of schools have chickens. These are things that we could calculate the rate that they're eating and how much this is going to cost, right? How much per bird am I paying? Um, and then the speed of walking or hiking so that you could figure out how long it might take you to take a hike down a trail. And then there's lots of examples on our signs of like speed limits. This was a sign about watering a tree. This is like those green bags that go around new trees. And you could figure out the bag holds, it says the bag holds 15 gallons of water. And maybe you could observe this and figure out how long it takes for the water to go be used, to trickle in. And you can find the rate of the water being used. And then rate also can bring in decimals super easy, just like measurement. Um, Easy always with gas. So when I go for walks in a very human built area, and I had teachers in both in New Brunswick that both were in, the city of New Brunswick, or in others that were in very rural areas. So if you're in a city, you can use that. Decimals, also power is often on a meter outside of buildings that you can look at and figure out. I would just like to look for and leverage any real life context for rate and decimals that I can. You can also measure things like maple leaf width and length, or any leaf or any natural thing, record it. Here I was making kind of like a graph, and then have them calculate the mean and the median, right? Again, we're kind of upgrading those skills using lots of decimals depending on how exact you want them, can give you different decimal points. So all things to consider when we're trying to get some of these higher level skills, practicing and linking to context outside, because that's a really important piece. And that is all I have for you today. 59 minutes and 51 seconds, I must say. Again, I am available if you have any questions now, as well as via email. And I encourage you to check out the resources. I do have fraction videos with those mud pies on my social media. There is some like random YouTube channel as well that my teen made and insisted that I have, and made some really ugly covers for. So you could check that out as well.
I think we had one really good question, but I think it's quite a broad question that can
Oh,
apply in a lot of different spaces. But she said, Amanda said, is there an age to start exploring this with students, or should they be exposed to it within the natural setting at any age? And she asked it kind of specifically during the arrays conversation and the factors conversation, where you kind of can see the progression as
yeah.
teachers, but what's the language that we use as we move through with kids?
I think it's not too soon ever to point out things in groups, especially and start using that language. I don't think you can be too young to give kids language, especially when we're looking at things like leaves or petals. Like, oh, this is a group of 5 petals. I think it's very age appropriate, even to kindergarten, first grade, to say that's a group of 5, and have them just kind of think about that, because they will be introduced to 10, right? A group of 10 very soon. I get to teen numbers very quickly. And so I think that's always appropriate. I would wait on the factors. I think it's also appropriate to talk about rows and columns and point that out if it comes up. Um, they know about graph paper, and graphs. We often talk about simple graphs. I think it's appropriate if it comes up and it makes sense. We can absolutely give that language. But it also, it shows you how when we start with that language, how it really builds on each other, right? Anything else?
Again, this was beautiful and wonderful and marvelous. We appreciate people keeping a few extra minutes at the end for this
Yeah,
this amazing chat. Next week's our last week, which
I
is a little
know.
sad, a last session.
I,
But yeah, assessment will be a part of that,
yes.
and yeah, and away we go. Again, recordings up by tomorrow at noon for sure. And yeah, someone just mentioned they're gonna have to go back to the recording because there's just so much
Yeah. And try extra.
embedded. Yeah, embedded in this. And then obviously exactly what Rachel said, give some of that stuff a try because that division of like when you muddle
It's
through
tricky.
things.
It's
Yeah, and when
tricky. And I
you
was running out of time, but I promise you it'll be like an aha moment. You're like, oh,
ping.
oh. And
Hmm.
you will have such a deeper understanding and it will pay off in the classroom.
So if you do it this week, we will chat. We'll ask you to pop it in the chat at the beginning of next
Yeah,
week,
yeah,
just
I'm
how
gonna
you felt.
remember that. Write that down.
All right, I'm gonna stop our recording for sure, and then